I'll add SF to it this time. There you go. All right, talking about doing spatial stuff in R. So as you found out the other day, current solutions for creating maps usually involve some kind of GIS software, things like ArcGIS or QGIS, open source version. There's some others out there too, eSpatial, Grass. These allow you to visually prepare a map. Pretty much the same approaches you prepare, like making a document or a poster. On the other hand, you have R, which is also an open source like QGIS, but doesn't cost you anything like ArcGIS. Software development environment that's used for computing statistical data and graphics, but it's programmable language. They have developed advanced spatial capabilities over the years, and you can draw a whole lot of different kinds of maps programmatically now, which is really nice. Oh yeah. Whereas you can think of a GIS like this type program as WYSIWYG, right? They like to say in the R community that what they've created is WYSIWYM. What you see is what you meant, or what you mean. So I'll go through a couple of examples. What kind of maps can you make in R, Aaron? Oh gosh, you can make all kinds. Here's one about London cyclist journeys. It's pretty nice. Here's another one where you can make the type of map where you're actually using the size of your marker to indicate some kind of level of measurement. In this case, it looks like it's nitrous oxide. For reports, you can also do something like this, where you're doing faceting, which honestly always confuses the heck out of me, but some people really like to do it. Want to do something cool? You can use something like GG Animate, where you can see that the two graphs are actually linked as one moves along. You see the proportions animating. You didn't see that down here, along here. And then up here, we actually have it animated. Something that's becoming quite popular lately on people's Shiny sites. And you can make interactive maps. This is a leaflet map on actually one of our dashboards that we've created for analyzing broadband data, the different types of measurements on broadband data and how they compare across the country. So here you actually see Oregon, and leaflet lets you then create something where you bring your cursor over it and you get pop-ups and you can read the attributes underneath. And then we can change the settings over on the left and get a different state at a different level. Here's one that we did with the Arlington County Police Department, actually trying to measure the impacts of a restaurant initiative they put together to do community policing on popular nights to go out. Should be seeing here that again, you can roll over things, and if things pop up, you can click in, zoom in, switch years, get different data sets, and start getting really interactive with what you're working with. Basically, a lot of different kinds of maps you can do. And of course, just doing something like a policy map, right? Here's one that we did with the Washington Metro, WMATA, when we were actually analyzing the amount of loss they were experiencing from people not paying when they get on the buses. Right? And part of what we wanted to bring out in that one was that, well, is there a relationship to economic vulnerability? So we came up with our own index, which you can see here, and came up with a really nice map which WMATA was unable to use. And a final example, lately I've been seeing people actually use ray shaders in R. So you're creating 3D environments. If you're somebody who's done any programming on gaming, trying to make 3D environments, you'd be familiar with what this is. I was kind of amazed that you can do it not too difficult a way now in R as well. Oops. Everybody make sure they're muted. Okay, I think I got you. All right, so spatial phenomena can generally be thought of as either discrete objects, you know, and I apologize, I just thought of, you probably got a lot of this yesterday too, but I won't be too long on it. They can be thought of discrete objects with clear boundaries or as continuous phenomena that can be observed everywhere. It does not have natural boundaries. So discrete spatial objects may refer to things like rivers, roads, countries, towns, research sites. Examples of continuous phenomena, things like temperature, elevation, maybe air quality. Spatial objects are, for the most part, and definitely what you will probably be working with, represented by vector data. Such data consists of a description of a geometry or shape of the object, normally also includes some additional variables. For example, a vector data set may describe the borders of the countries of the world, which is something we'll do later. In other words, a geometry, but may also store their names and the size of their populations along with it for a specific year. Right? Or the geometry of the roads in an area, as well as their types and names. Right? These additional variables are often referred to as attributes. Right? The continuous type data, continuous spatial data, is usually represented with what's called a raster data structure. So here you see a satellite photograph from the USDA cropland data layer. They're actually showing, right, you have color coded on what's covering all of the acreage out there. It's digital aerial photographs, imagery from satellites, digital pictures, sometimes even scanned maps. That's where you in the simplest form, raster consists just of a matrix of cells organized into rows and columns, or a grid, where each cell contains a value representing some information, such as temperature. So raster data is commonly used to represent spatially continuous phenomena, as I said, things like elevation. Raster divides the world into this grid of equally sized rectangles, referred to as cells, or in the context of satellite remote sensing, they'll say pixels, that all have one or more values for the variables of interest. A raster cell will usually represent the average of some measurement for the area it's covering. I've seen times when it doesn't, but that's usually the case. In contrast to vector data, in raster data, the geometry is not explicitly stored as coordinates. Right? It's implicitly set by knowing the spatial extent. I'll teach you what that word is in a little bit, and the number of rows and columns in which the area is divided. So from the extent and the number of rows and columns, the size of the raster cells, which they call the spatial resolution, can be computed. Right? Now you could think of doing something like this with polygons, right? If you think about it, now you're talking about tens of thousands of polygons that are all being processed at once. And it actually gets to be a lot more efficient to do it as a raster, basically a digital picture, right? Okay, so vector data. When we're talking about points, lines, and polygons, we're talking about vector data. In all cases, the geometry of these data structures consists of a set of coordinates, x's and y's, right? Points are the simplest case. Top there, each point has one coordinate pair and n associated variables. For example, a point might represent a place where a rat was trapped. I don't know why I worked on that example. The attributes could include the date it was captured, the person who captured it, the species size, maybe the sex, maybe information about the habitat. Right? You could also have multiple points all in the same structure and still be vector data. So lines obviously are composed of at least two vertices or points that are connected. For instance, a road system or a stream may be represented by a line. This line is comprised of series of segments. Each bend in a road, right, is going to be another vertex with an XY location. And then there's polygons, is what you're going to end up working with the most, consisting of 3 or more vertices that are connected and quote unquote closed. Right? So thus you're getting the outlines of plot boundaries, lakes, oceans, states, counties, census tracts. These are things we most often represent with polygons. I'm sorry. Somebody's having an issue with getting a pull from the training repo. I don't know if anybody could lend Jesse a hand while I keep going. Shapefiles, that's a term you're gonna hear a lot. What is shapefiles? Well, when you take a bunch of points, lines, or polygons, and you put them into a file, you have a shapefile. But these shapefiles they often come along with a set of attributes. So when you download shapefiles, don't be surprised if you're actually getting 4 or 5 files at once. The one that's .shp is the shapefile. Everything else, if you load that, will come in and be associated with it. Always something that's a little confusing first. So spatial data attributes, right? Each object in a shapefile has 1 or more attributes associated with it. Shapefile attributes are similar to fields or columns in a spreadsheet. Each row in the spreadsheet has a set of columns associated with it that describe that row element. In the case of a shapefile, each row represents a spatial object. Right? For example, a road represented as a line in a line shapefile will have 1 row. And then all those attributes associated with it. These attributes can include all kinds of information that describe the object, things like name, length, number of lanes, speed limit, you name it. Extent. This was a word I used before. What does extent mean? So I've already said you're going to get a geometry. You have geometry, you have attributes, and you have extents. Okay. When you're talking about spatial data, extent basically means the zoom box that you're zooming into. Right? Often called the bounding box or the B box. Now, you can start with some vector data of the whole world, but all you really want is 1 state in the United States, right? So you're going to define that extent. I'm sure Chris covered the perils of the coordinate reference system. Right? Coordinate reference system refers to the way in which spatial data represent the Earth's surface, which we know is round and 3D. What we do with it when we flatten, so that we can draw things on a 2-dimensional surface or on a screen. However, there's a bunch of mathematical approaches, and each one ends up having a different result. Right? We have to choose what's best for the application at that time. Here is an old picture that I always liked that just shows 4 different ways of mapping the human head: globular, orthographic, stereographic, and Mercator. And you notice the one that looks the oddest probably is Mercator, and that is also the one that you see the most when you're thinking about a map of the world. So things are a little bit distorted. Here's just a projections, 4 different projections of the United States. Right? See, sometimes it's squishy, sometimes it curves up to the right. The Mercator, again, is probably the one that we see the most. They're all correct. Here's a little couple-minute video. Many of you may have seen this, but if not, everybody should. I'm sorry if it's too loud. Okay, well, that's probably enough to get the point across. First thing, I think just the dimensions are exciting enough without the snazzy beats, but I guess together they're awesome. No, don't start again. Okay. So spatial data formats are confusing. I wanted to get that out there. I mentioned .shp shapefile before. GeoJSONs are also very popular in web programming. Gpackage, becoming more. You'll get stuff in CSVs. TIFFs, when you're getting raster data, they will almost always come in massive TIFF files. But that's not all. You actually look at the, go to the site for the Geographic Data Abstraction Library, which is what's underneath SF and everything else when it's actually trying to read things. You'll see that there are literally hundreds of different file types that can be used. I think Chris mentioned yesterday that if you actually wanted to cover everything that you could do, the GIS system, it's more like an encyclopedia as opposed to a simple book on a shelf. There's a lot you can do. But for our purposes, luckily, and fairly recently, this is all you basically need to do to read most of the vector data that you're going to need to bring in. You're going to need the SF library, and you're going to go stread, and that will be it. Right? And this is what you get. You get a nice, tidy SF data frame. Right? You look down at the bottom of this, right? What am I seeing? I'm just seeing a data frame, right? I'm just seeing a table of data with columns. Right? Now, one of those columns, though, geometry. Right? This is what's called a list column. This is what is what SF improved in spatial stuff for R. You used to not be able to have a list of multiple things that you could easily extract in a single column in R. But now you can, which means For every entry, I can have all of the geography. If I have a polygon that has 6,000 vertices, that'll all be in that one cell now. What that means is that you can actually start working with these just like you're working with any other data frame or tibble or data table, whatever you want to call it. Right. You will also notice, though, they put some attributes, some metadata on top of this in an SF data frame. And here we go. We have the geometry type, right? Points. This is a bunch of, we don't see X, Y's, X, Y's. This is just a bunch of points. Okay. Remember I talked about the extent or the bounding box? That's what the B box is. It's got your X, Y minimums and your X, Y maximums. That defines the box around. EPSG, remember I was talking about the projections, the coordinate reference system, right? This one doesn't have one. Why doesn't it have one? Because we're just talking about lat long points on the globe. Which means this probably wasn't the best example I should have. Next time I'll put in one that actually has one. But as you can see, geometry, bounding box, the projection, right? And then a table of attributes. It's basically, that's what's inside an SF data frame. Any questions yet on that? If not, we will move on now to what you would do with that SF data frame. So one of the big things people do is they use it in conjunction with ggplot, which is something that you linked previously. So let me stop this share. And switch to this one. Okay. Give me a second to bring the other boxes up. Thank you. Oh. Okay, in the repo, if you don't pull, under number 11, data exploration, number 2, geospatial, there is a folder called GIS in R, and inside that it is gisinr.rmd, an R markdown file. At the top of the R markdown file, I have a bunch of commands for output that I'll talk about a little bit later, why I've done that. You'll see in the end. As we know in R markdowns, I can just run any chunk by pressing the play, and you're loading all of the libraries. You don't see GIS in R. Have you done a git pull yet? I'm inside training. Oh. Is anybody else not seeing the GIS in R? Same. Oh my goodness, what happened? Okay. Well, one does have it. If you're one above that, if you're just in the O2 geospatial, is there a GIS and R markdown file? Okay, that's great. If you guys can help each other. If not, this isn't too long. I'm going to walk through building a couple maps and show you how you do this with ggplot and SF. And this is all available, right? And you'll spend more time doing this, honestly, in the data camp, learning the specifics. Get stashed before pulling. Yeah. My limited doing Git for a couple years, and at least once a week I Git stash something so that it works. Okay, so I have loaded my libraries. Okay, and now, so let's talk about ggplot2. You learned it implements a grammar and graphics, right? What it really means is gives you a higher level of abstraction where I can add layer by layer by layer. Okay. SF is the current state of the art of spatial objects in R. I was asked previously about SP. That is the old way to do things. That was the way that I learned. And it involved using a lot more libraries and a lot more special techniques. Recently, after I'd say about a year ago, ggplot2 has started to be able to use the simple features that come from SF as layers when you're building those layers in ggplot. Right? So therefore, you can programmatically create maps using the grammar of graphics, which is cool. So let's get started. Okay, first I'm going to load ggplot2 and SF, which I already have. I'm also loading this theme set from ggplot2, theme BW, because it looks pretty good for maps. These packages are Natural Earth and the are Natural Earth data. They provide a map and attributes of all the countries in the world, which is nice. So here I'll load them, do these one at a time. Now you see I have the data frame of the world. If I look at the class, it's both the data frame and SF. And sure enough, I do a head on it. As you saw in the slide, here are all the attributes, including a geometry column at the end. And here's the metadata, multi-polygon, the bounding box, and here's a coordinate reference system. GS84, very popular. All right. So this first part, I'm going to cover fundamentals of mapping using ggplot2 and SF, presenting basic elements and parameters that we can play with. First, we're going to start off by creating a simple base map in ggplot. So as you should be familiar with ggplot, you can put the data in as the first item in the ggplot function. And then with the plus, we can then start adding different levels to it. Right? This geom SF is the special layer tool for geometries that now ggplot uses. I want to run the whole thing. Aha. Data world, and all I had to do was say, use that geometry column that was in there and make a nice map of the world. We talked about that. Okay, now we can start adding start building this map, making it look nicer. Right. You can start doing things like adding labels for the X and Y dimensions. And we can add titles. And in this one, I'm actually dynamically reading from the data the number of unique entries to be able to post, because I'm pasting when I say that many countries. If I run it, boom, there. I have the dynamic number, 200 countries up there, latitude, longitude, and I have a title, world map. Okay, next I'm going to add some color. And these are attributes of the geom_sf function. Color for the lines, and then the fill. Okay. There we go, got some black lines, and I got light green filling in all my countries. Okay, we can do more complex color schemes. Okay, here's another one that uses the Viridis colorblind friendly palette. Okay, which I am colorblind, and I love the Viridis colorblind friendly palette. I can actually see those things. Pastels, trying to avoid so many pastels for my sake. So we can see what we're doing here. Another thing I can do with the geom_sf, I can give it an aesthetic fill with the population estimate. Then I have a cool function here. Comes with Viridis. I can scale it using a function, using a transpose function, in this case, square root. All right. Now run it both ways. Okay. Because of the massive differences in some of the countries, the scale for coloring doesn't break it out enough. Using the square root, a little easier to see what's going on. That's all I'm trying to do there. All right, the coordinate system. Using coord_sf, we can deal with the coordinate system, which includes both the projection and extent of the map. By default, the map will use the coordinate system of the first layer that defines one. This is, when we're building these things, we're going top to bottom. Or if none, it will fall back on the WGS 84, which is the reference system used in GPS systems. You can override this by assigning your own, such as down here we set the CRS. This big long text is called a proj4 text. You don't need to know that, really. But this one in particular, there I changed that world data and I now have a globe. This is the European-centric ETRS-89 Lambert azimuthal equal area projection. That is a mouthful. Luckily, the European Petroleum Survey Group, EPSG, came along and turned all of these long things into some reference numbers. So we can use these instead. Both of these give us the same thing. I can say CRS equals this plus a nit equals EPSG 3035. SF also has a function for it, STCRS 3035. Right. And those will both give me the same thing. Back and forth, it's the same thing. much easier to use. So you can also set the extent in there. In practice, allowing us to zoom into the area of interest. I run that. Okay, I've zoomed into the Gulf of Mexico. See now, any other processing I do below this, it's only going to process inside that extent. All right, you can do some cool things with other packages like GG Spatial, things like putting on scale bars and north-facing arrows. Right? There's a lot of different settings that you can use to do these. Let's see if I just. Okay, I'm starting to get my scale bar on there now. And I can also add in my little north symbol. And then remember, I really only want it for the Gulf of Mexico, right? So note this warning up here. Right, it's warning about the inaccuracy of the scale bar, right? Since the map is unprojected data in longitude, latitude on an equidistant cylindrical projection. Basically, the bigger this map gets, the less that this bar is going to be accurate, right? Because it's assuming a flat world, but we know that it's curving underneath it. But works perfectly. That's why you usually only see those bars, like when you zoom in on Google Maps when you get close. It's going to become accurate. Okay, let's try country names and other names. We can use geom text and we can use annotate. We can add all kinds of things. Let's see, what did I do here? Okay, I'm getting the centroid of the countries, and then I'm adding in coordinates to the data frame. So, see what that looks like at the end. Right now, world points. And down. Ooh, lots of things. All right, I have all of those points. Centroids. Now I want to combine back. So what I did here was made those points, but now they're X and Y, and I brought back the geometries of the countries. So everything's in there now. Now using the function geom text, I can add some text labels, give them some colors, fonts, check overlap if I want to. If there's something that isn't in the data set that I want to put on there, that's when you use annotate. So in this case, I'm going to put Gulf of Mexico to know what we're looking at. And again, you end it with the extent. Let's see what we got. All right. Now we have countries with names set on their centroids for that country, and we've added in the Gulf of Mexico as an annotation. All right, now we can make some final touches to make it a little bit more appealing. I can add back in my bar and my north arrow. I can get my titles right, and I can do things like use the theme function, which has 1,000 things you can set, like the panel background. Right? Since we're dealing mostly with the ocean here, let's make it blue. All right, now we're getting everything you need to have on a map. All right, say I was happy with this. I was ready to put this onto the website or onto a poster or into a report. GG save. Right. Very simple to use. It just reads off of the suffix that you give it. Right. So here, if I want to GG save a PDF, look over in my files now. I now have map.pdf. Click that. Sure enough, there's my PDF. Or if I needed a ping, I can set my width, height, as well as my dots per inch. Now, if I look over in my files, I now have a ping file as well to use. All right, so cool. Now let's add some additional layers. Get fancier. Start working with some points and polygons. On this previous part, we presented general concepts of the map, little information. Right. Now we're going to start to successfully add more and more layers. So let's say, for example, we're studying, it's 2 research study sites according to their longitude and latitude, and they're stored in a regular old data frame. So here I create a data frame with 2 longitudes and 2 latitudes. Right. Let me show you something here. All right. This is just an aside. You may have been wondering why it starts with parenthesis here and ends, right? It doesn't need to, right? I could just assign it to sites and then do something like head sites to see what's in there. And RStudio, you can, in these chunks, if I put those before and after the whole thing, it will automatically display for me, which is cool. All right, quickest way to add point coordinates is with the function geonPoint. Works on any XY coordinates, regular data points. As such, we can adjust all characteristics of points. For example, the color of the outline and the filling shape, etc. In this example, here we're going to add 2 diamonds. So this is the same as before. I'm just creating my layer, but now points, and I can set its data source. Right? I can start setting aesthetics for it. Shape number 23 is a diamond. I'm going to fill it with dark red. Right? If I only run that part, though, right? It's a diamond over here around Florida, right? Because I didn't use the extent yet. There we go. I'm really looking at here is Florida, down in the roughly Miami-ish area. So a better, more flexible alternative to doing that is to use the power of SF, converting the data frame to an SF object. It allows us to rely on SF to handle the on-the-fly coordinate system, both the projection and the extent. It's going to be very useful. So now I'm going to take the sites data, latitude and longitude. Where to go? Yeah. And I'm simply going to tell it which columns, what the column names are, where the coordinates are for longitude and latitude. Another thing to note as an aside, I know in our in the English vernacular, we often say lat-lon, latitude, longitude. GIS world, it's the other way around, longitude, latitude. Right. If things look like they're completely cattywampus when you plot them, make sure you got them longitude first, latitude second. Here I can set the coordinates. I can also set the projection. Oh, I have that in twice. It's the same thing. This is just a default. Okay. And there we go. Now I have an SF data frame. And I use the st as SF function from the SF library. All right. So moving on, let's go ahead and plot that. Okay, cool. Still working. All right, states. If I look on here, we know there's more than Florida on here. All right. So we want to add more governmental administrative information. Okay. Library maps is useful for this. It has a lot of that information in it. Okay. I'm going to take the map function from maps and say, give me states. Don't plot them. You can fill them, but don't plot them. Just give me the states. And then I'm going to use st as SF to turn it into an SF data frame and then take a look at it. All right, cool. So now I have an SF data frame that has an ID column, which is all the state names, and geometries representing those states. I said state names are a part of this data, the ID variable. Say, what did I say here? Simple, not necessarily optimal way to add state name is to compute the centroid of each state polygon as the coordinates where you want to draw them, just like we did before on the country names. Right. All right, this is basically what I did up above. All right, now I have an XY for a centroid, and I still have the geometry of the state. Good morning. Yes, you'll always get warnings, which is nice. When you're getting too big to be close to exact. In this case, it's fine for our purposes. You'll notice that the states are lowercase. So here I use the tools library to use their to title case. Another capitalized. Okay. So to continue adding to the map, state data is directly plotted as an additional SF layer, again using GeoMSF. So it's a thing in ggplot. You don't only have to use one. You can use as many as you have, as long as you have agreement in the coordinate reference system of them. It'll plot them even if they don't, but it'll look crazy. Right. So here, I'm plotting the world. I can add another one with data, the states, right? And then add text and an extent. There we go. States and names. All right. Now, we don't see the South Carolina one here, and these other ones are up by the edges. So we can use, ggplot has a nudge function, right? So we're going to create some variables in our states data frame, SF data frame. I call them nudge y. Everything gets a -1, which is makes everything go south. And then we're going to adjust for Florida and South Carolina separately. All right. So those will be used. And also, I'm going to go ahead and draw a rectangle behind the state name using geom label. See what we get. All right, so now I see South Carolina. Everything's moved a little bit. Not great, but better. And I have a box around the name so they're easier to see. All right, counties, polygon data. County data is also available from that package maps. Also, a lot of the data that you'll pull down for all different types of recents for your projects will be at the county level, if not at a lower level. Here I'm going to do the same thing, creating my SF out of the county boundaries. I'm going to subset these to Florida and make sure they're numbers. All right, looking good. Now I can add my county lines. Cool. Let's see. Yeah, nudge is awesome. I agree. All right, got my county lines. Wouldn't it be nice if we could fill these in so we could easily identify which ones are the largest? For this, I'm going to use the Viridis colorblind friendly palette again, but I'm also going to add something, some transparency to make it look nice. All right, so here's the scale Viridis function. Alpha is what sets the transparency here. All right, now we're starting to look nice. What else could we add? We could add cities, some point data. All right. So I could create Florida cities by simply creating my own data frame. Right? State Florida, repeat 5 times. These 5 cities and looking up their individual latitudes and longitudes. Right? Great. Obviously, that's not really the way we want to do things. That would take forever. That's why the package TMAP tools is really nice, because it has a great function, geocode OSM, which allows us to retrieve geographic coordinates from any address using the OpenStreetMap API. Right? You may have done this with the Google API, but Google API requires that you have a key. And if you go over a certain number, you're going to start paying for it. OpenStreetMap is open source, free, and getting better all the time. I'm not going to say you can completely replace using Google for some reasons, but the longer it goes on, the better it gets. And for most things, it's pretty darn good and free. So here I can load my TMAP tools, and I'm just going to send in the names of the cities, the geocode. Going out, this may take a minute. All right, there we go. Give me back my lats and lawns. Pretty cool. Okay, now let's convert that using ST as SF, like we did before. We're going to choose the CR. We're going to choose the projection for it here, and we're going to tell it where the coordinates are. right? They're in the lon and lat columns. There we go. Have a nice SF data frame to work with. All right, so let's add those city locations and names on the map. Right. So you can see I have the base map and I have the counties. Right, now I'm going to add the cities, and I'm going to give some instructions to how we should label the cities that are in there. Right. You notice here, call X is lon, Y is lat. Label equals query because that was the name that came back. Right, you could rename that to name if you want to, or just leave it. Now let's see what we get. Ready. I've got a map with counties and some key cities to keep myself oriented. Right. This isn't great because it kind of confuses with all the county lines. It's kind of messy. Right. So can we fix that? Yes, we can. We can use a great function called geom text repel, which is nudge away, dynamically nudge away. So that I can get something like this instead. Much more readable. Okay, now for our final map, we'll put all of that stuff together, right? Bringing back my counties, my states, my sites, my outlines. Make sure I've got my cities. Make sure I've got my my counties colored in but transparent. Remember this one? Now I'm going to add back in my distance line. I'm going to add back in my arrow. Right. I'm going to retitle it. Oh, here's where I bring in my theme, where I can do things like the fill, the blue for the background. Let's see what it all looks like in the end. All right. Now we have a pretty decent looking map that we can use in many places. Okay, so that's a demonstration of using ggplot2 and SF together. But before I let you go, I did want to show one other thing, which is that I've been loading all of this SF data from local files using the read. I wanted to show you here that you can also use stread to read them from anywhere. So in this case, here's an open data site that happens to have all the hospitals in the country. Right. And you'll notice this is a GeoJSON link. This isn't a shapefile. It's one of those other ones I talked about. You can go out, read that in. What's that there? Okay. Look up here. Now I have 7,596 hospitals. Good stuff. Okay, I'm going to limit this to just Iowa. Take a look at what I got in there now. Good, looks good. What's the class of that? Yep, read it in. It's an SF and a data frame. Excellent. So now I can very easily plot that. Probably should have put the outline of Iowa in there, but you can kind of tell where it is. Right. I was able to color code it to the level of trauma facility that it is, and the size of the dot indicates the population of the area. What I really wanted to show was that something as simple as reading that in subsetting, and plotting. You're starting to do some mapping in R very, very quickly. Okay, lastly, big finale. If I click knit up here and cross my fingers, this should now create me an HTML page. You see it creating some more files over here. Dash and files. 69%. All right, we're going. There it is, going out to the open street map. $100. That's awesome. All right. So what did this give me? I'm going to move this. Okay, so when I knitted it, now I have a whole web page going through everything that we just went through with the table of contents on the side, so I can jump to the different parts very quickly. All right. That is, I said I'd say what it was for. Get up there. That's what I was setting up here, up top in the output. I was saying, give me a table of contents with a depth of 2, not collapsed. Right. And in this case, if I created a PDF, if I knitted it to a PDF document, it would also have a table of contents in it. My suggestion is that you take this, and then as you learn more and more about doing spatial work in R, start adding your own down at the bottom, right? And it will start building your own headings in the table of contents. And then you'll have your own very easy reference system to go back to.
Hey, Aaron, can I ask you a question?
Yeah.
Hi, I'm Heather, by the way.
Hey.
Do you, off the top of your head, know if there is a way to outline like a river, if that data is in that mapping function, or if that's something we'd have to do by hand?
Well, you definitely shouldn't have to do it by hand.
More like manually, like finding plot like points, like latitude and longitude points, and having those plotted on there, or if any of that data is available somewhere.
Well, definitely, you can definitely get Latin lines of lines representing rivers. The problem is that they're usually lines, right? They're not. It's not a polygon, and so then programmatically, you would have, if you actually wanted to give it width.
I don't so much care about the width. It's more of like, do you know if the line would be fine? But I didn't know if that kind of data was in there.
Oh, absolutely. Yeah, you can definitely get that kind of data.
Okay, and that's in the mapping thing.
That wouldn't be in that.
It'd be somewhere else.
It would be somewhere else, right? That'd be a Google search on shapefile for rivers in Indiana, and you should be able to find it.
Okay, OpenStreetMap extract.
Oh, there you go. OpenStreetMap.
We'll talk about it Tuesday, OpenStreetMap a bit, so you can maybe get some ideas from it then.
Or as Jacob has pointed out, the National Hydrography Dataset from U.S. Geological Service. That is their job, rivers.
Which isn't super accurate at a local level, but it's still cool.
Cool.
A lot of the maps imported by Leaflet have like the background rivers and lakes and all that already built in as well.
Yeah, and Leaflet, that's actually the background tiles, right?
Okay.
You can choose which ones you want. In fact, we will talk about Leaflet next week, I believe. Which, at least in my work, I'm either using ggplot with SF for documents and posters and the like, static images that are output, but all of those dashboards that I showed you at the beginning, that's all leaflet. Okay? It's just another way to output things. But we will talk about those later. Oh, Natural Earth has them too. Okay, great. Yeah, there's pretty much anything you want geographically. There's generally multiple multiple places to go get them, which is terrific. Okay, any other questions? Okay, well, I hope this gave you a good overview of how you could start using R for spatial stuff, and hopefully give you your own little reminder tutorial that you can go back to at any time. Okay. And with that, I will say thank you to you all. Now you should be using the remainder of your time to get on and go through the SF tutorial using SF in DataCamp, which will go through a lot of different examples now that you have a good understanding. Okay. All right, thanks everybody.